Welcome back, students. We will start with the next unit of unit number 5 in transducers engineering, and this is our last unit. We have already covered the resistive, capacitive and the inductive sensors that we can use for several different kinds of applications, which we have seen in elaborate details in the previous sessions. So in this, to the last unit, we will see there are several other transduction mechanisms available in the industry or else in the nature, which can convert some form of energy to the electrical energy or other form of physical forms of energy. And in this we are going to see some few examples that are most commonly used in our day-to-day life or in our industrial applications. To start with, I will first start with the used up piezoelectric transducers. These piezoelectric transducers have already been introduced to in several different cases. One major case is the ultrasonic production, ultrasonic transducers. Ultrasonic transducers, where we are using this piezoelectric transducers to produce the ultrasonic acoustic range frequency. So these piezoelectric transducers are the ones which produce or convert the mechanical stress to electrical energy, or either the vice versa, that is the electrical energy to the mechanical energy. When we convert the mechanical energy to electrical energy, we are able to say that that is a direct piezoelectric transducer, and when we convert the other one, the electrical energy, to the piezoelectric or the mechanical stress, then it is the inverse transducer, that is for the production of ultrasonic waves. So in an ultrasonic transducer, we will be having a transmitter and a receiver. As I already explained you, in different types of applications, in a level or an obstacle detection, let us take it's an obstacle, this is a transmitter and this is a receiver section, and here in the transmitter section we are going to give in electrical signal which makes it to vibrate or produce ultrasonic frequency range, and here it gets hit over to the obstacle and it returns back as an echo, and it is received by the receiver, and there it is being converted to an electrical signal. This is an electrical output. Okay, so this is the main application of an electric and piezoelectric transducer in ultrasonic production. Okay, like this there are accelerometers which can be used for using the piezoelectric transducer, like this the seismic activity. All these things you will be studying in your industrial instrumentation in your coming the next semester syllabus, where there will be having a seismic mass. This will be your seismic mass will be the piezoelectric crystal which will be accelerated, and from there you will be able to get the direct acceleration possible. So this is one of the main transduction mechanisms which is not falling into the resistive, capacitive or inductive, but it's a very important transduction mechanism that is needed in the industry. The next one is our most interesting magnetostriction. Magnetostriction transducer. What is this magnetostriction? It's a very peculiar name that it's a very simple thing. The magnetostriction is again can be told it is piezomagnetic. When you apply a magnetic stress, a mechanical stress to a material, then there occurs a change in magnetic field. In this kind of an effect is seen in some ferromagnetic materials. That is, when you change the magnetic field, there is a proportional change of mechanical stress. This is what happens there. Okay, this can be also the change in the, like in the inverse, something like mechanical stress is changed, there will be a change of the magnetic field that is present inside a material. For example, I just take cantilever beam. You want to find out there is going to be a air flow or a force that is being happening there. The airflow, this is going to hit this very thin sheet of airflow. If you want to find out what's the flow that is happening over here, let us fix a magnetostrictive material to this end of the sensor or end of the beam where it is fixed. Okay, when it is taken away, okay, then the magnetic property will change, and when it is coming nearby, then the magnetic property will reduce. So depending upon the increase or decrease in the magnetic property or the mechanical, because the mechanical stress of this cantilever beam directly affects the mechanical magnetic property, which is present here in the transduction. Okay, so this kind of a transduction where the mechanical change occurs directly results in the change of magnetic permeability, then it is called as magnetostriction. The third one is a fiber optic transducer. Okay. What is fiber optic transducer? Okay, let's first get introduced to what is fiber optics. Okay, this is your fiber. Okay, it's called as a core and outer ring. You imagine a ring surrounding this fiber. Okay, and this is the protective layer is called as the cladding. And when you pass light through this, both or this core has one kind of a refractive index where light can pass through this, and the cladding has one type of a refractive index so that it don't allow light to pass through this. Okay, so this is little bit transparent to light so that it can pass through this, and this is opaque to light so that the light don't emerge out. Okay, this is the major construction or a basic construction of a fiber optic cable. This is a fiber optic cable. Okay, I would say this is a fiber optic cable. We are not going to enter into the sensing mechanism now. This is the fiber optic cable. Okay, so I will just enlarge this. You are going to, we have a light source here. We are having a light source here. Okay, and light enters. As because it has a very critical refractive index, it is passing inside, and it is not, this cladding is not allowing the light to pass out, so it starts to reflect inside like this. Okay, and finally it comes out, and here we have our detector for our fiber optics. This is a source, this is the detector. The source may be any LED, laser, whichever you want can be taken for the light source. Depending upon the applications it will change, and the detector will be any kind of detector, photo detector. Okay, any kind of a photo detector. Okay, this also may be an light dependent resistor, or else a photodiode, or else a transistor, or else a photomultiplier. All these things are these photodetectors. So now we have seen what is the major principle behind the light passage, that is the refractive index is same over inside the core and we are getting it outside, because and this phenomenon is called as total internal reflection. Okay, let us take an intensity of light is an intensity alpha enters, okay, x enters the source, from the source, and you expect the same intensity x outside. Okay, if there is a total internal reflection happening and there is no loss of light inside the fiber. Yeah, true. The same x what is given in should be coming out. Okay, but this doesn't happen. If there is going to be any bent or any kind of bent is going to happen there in the fiber, then the refractive index will change and you won't get the, and again the same kind of an amplitude what you have given to the fiber, and this reduction is called as the noise. Okay, but we are going to utilize or exploit this property for converting this cable into a sensor. Now imagine the same kind of a cable, okay, fixed cable, and you are applying a pressure. Okay, there will be a bend happening there in the fiber optic cable. Okay, then you are giving in a signal, already giving a signal, and without application of this 5 newtons of pressure, let us imagine, then you will be getting x, but there will be a reduction of amplitude, okay, this y, okay, when you apply some pressure because of this refractive index change. Okay, so this refractive index change makes this happen, and this y, which is the noise, which is the inside, that is the refractive index change because of which the noise have occurred, this is proportional to the amount of force that is applied. So this can be a force or a pressure, and all those things can be there. So whenever there is a change in refractive index, now this becomes a sensor to detect the change of the same property occurred. So this is like this, we can create innumerable application in the fiber optic cable so that we are able to read those parameters. So these are some of the major applications in fiber optic sensors, and then we have seen the piezoelectric transducers and the magnetostriction transducers. Thank you very much, and we will see in your next session in unit number 5. Welcome. Thank you. Bye. Semiconductor sensors, and the next one is our digital transducers. Okay, so these two are very simple topics, and we have already seen these things in our previous sessions. The first one is our semiconductor sensor. The semiconductor sensors are the sensors which are using the silicon or germanium or some kind of oxides of silicon and germanium, SiO2, GeTi, okay, all this kind of semiconductors are used in the manufacturing of these sensors. I will tell you a simple example there where we have used these things, LM34 and LM35. Okay, these two are temperature sensors which are used for the measurement of temperature. Okay, and these are very cheap sensors which are used in the measurement of temperature. We have already seen in the resistive property that we can use RTDs, that is the resistance temperature detectors, and thermistors for the measurement of temperature. And instead of those things which are a little bit expensive in nature, we can go in for mass production, and for easy productions we can go in for semiconductor based sensors, that is LM34 and LM35, which consist of a very small amount of a silicon piece inside the sensor, which looks very small like this, yes, very small, like a pepper round. We have a semiconductor sensor. Okay, so this is the major advantage of a semiconductor sensor. These are temperature sensors, majorly I am saying about it here, but there are several different kinds of sensors also available for measuring of acceleration, velocity and all this. But this LM34 and LM35 are temperature measuring sensors. These are semiconductor based sensors which utilize Si, the silicon, germanium, silicon oxide, titanium, and the germanium oxides. And the advantage of using of the semiconductor sensors are the very small, like a bulk manufacturing is possible, and apart from that they are very cheap. The next one comes as a digital transducer. The digital transducer, as the name implies, it gives an output which is directly digital in nature and not the analog output. Okay. So when we get a digital output, we don't need to have a data acquisition system that converts the ADC, that is the analog digital conversion mechanism, is not necessary, and we are going to get directly the digital pulse which we are going to feed inside a computer or a microcontroller or microprocessor kind of a mechanism, so that we can control the circuit easily. So this is a digital transducer where we don't need an ADC for the analog to digital conversion. So I will tell you a simple mechanism. Imagine a Bluetooth. Imagine a Bluetooth wheel, a toothed wheel connected to a motor shaft. Okay, and here you have a source, and at the other side you have a detector, photo detector. Here, this is a photo detector, this is a light source, and this is connected to a shaft of a motor which is rotating at an RPM. Okay, now when the rotation is happening, okay, this tooth will cut the light source. Let's imagine this light source is a laser diode. So exactly there will be a ray of light going and hitting the photodiode. Okay, and whenever there is a cutoff happening because of this tooth, okay, then there will be a total zero happening, or a voltage will go zero in the photodiode, and when the exposed region comes into picture, then we can say that it is being exposed. So you will get something like this. When there is going to be a total cutoff by the tooth, you will get a bottom line. Then when you get a total penetration through the shaft, then you will get a line like this. Okay, something like this, a clock pulse will be formed. Okay, and here, just for an example, some 6-7 pulses are equivalent to one rotation. So this is equivalent to 1 RPM. Okay, this is 1 rotation per minute. Okay, so like this we can calibrate the sensor to any kind of rotations, and here you are going to get a direct output, and this can be fed inside a microcontroller or a microprocessor. So this kind of an sensor is called as a digital transducer, and here I have showed you a measurement of angular velocity based digital transducer. As I told you, it's a very short session, and we have completed our semiconductor based sensor and a digital transducer. Thank you very much. See you in the next session.